And what I'm hoping to do this afternoon is to talk about Reissner-Nordström and also talk about Kerr. And we'll see how much of that I manage to do. Boy, I'm out of chalk. One piece here. Okay, so the Reissner-Nordström black hole is, rather straightforward generalization to the Schwarzschild black hole. So we're still, staying within the confines of static spacetimes. So we don't change that. We don't change also the spherical nature of the space-time. The only thing that we do that's different from Schwarzschild is to allow the black hole to have charge. So what we would imagine here, physically speaking, is that, well, instead of having the collapse of a star that would have no net charge, well, we just make sure that the star initially collects up a macroscopically relevant amount of charge, and we let that collapse to form a black hole. It's certainly not very realistic from a physical point of view, because no macroscopic forms of matter will ever acquire a lot of net charge. I mean, if it does, it will tend to attract the opposite charge pretty soon, and overall the matter distribution in the universe is neutral. But nevertheless, we can imagine that a scenario like this happens, and we can see what happens in terms of what this does for the structure of space-time outside and inside the black hole. So keep in mind that we're doing here, we're still talking about a black hole that could conceivably be produced by gravitational collapse, but it's a little bit unlikely that this would happen naturally in the real universe. So we have a black hole that will be, characterized by two numbers. It will have a mass and it will have a charge q. There's a uniqueness theorem for the Reissner-Nordström black hole that's, that's a direct generalization of the uniqueness theorem we had for the Schwarzschild metric. And the idea there is that if we have a space-time which is not vacuum anymore, but a space-time that would have a distribution of electromagnetic fields outside of it, if we have that, if we have asymptotic flatness, if we have a smooth event horizon, and if we have a static space-time, then the statement of the uniqueness theorem says that, well, that space-time has to be spherically symmetric. That's not an assumption, that's a result. And then it has to be a piece. It has to be a Reissner-Nordström solution. So we have both the Birkhoff-type theorem that says that if we have spherical symmetry, the outside, if there's charge present, the outside is going to be a piece of the Reissner-Nordström solution. But we also have an Israel theorem that says that if all of those ingredients are in play, spherical symmetry is something that comes out as a result, not as an assumption. And the resulting black hole after gravitational collapse will settle down to a Reissner-Nordström solution. In the book, I actually derived the solution, and the idea is pretty simple. I'll just go through a sketch of a derivation that hopefully is fairly intuitive. The idea is that, well, we have a charge, and therefore we have an electric field that will be given by the charge over the radius squared. So here the distribution of charge inside the star is spherically symmetric, which means that the electric field outside the star is as if all the charge were at the center, and we get the usual 1 over r squared field for the electric field. I'm using a Newtonian, argument here, but in fact, all of that can be made rigorous in general relativity. But I think you'll see the ideas very clearly if I do it in a sort of quasi-Newtonian way. So we have a charge, we have an electric field. The electric field, of course, has an energy density associated with that. The energy density in the electromagnetic field, given that we don't have a magnetic field here, is simply going to be the square of the electric field divided by 8 pi. That's the standard expression for the energy density of an electric field. And if I make the substitution, then we get q squared divided by 8 pi r to the 4th. If we have a distribution of energy density, of course, this will affect the structure of space-time outside of that body. So I'm talking here about the solution that we might find, the metric that we might find outside of the charged body, which eventually will be collapsed to form a black hole. This will affect this, this will create some space-time curvature outside the black hole, and in spherical symmetry, you can actually write down the Einstein field equations in a form that involves a mass function. I think you're aware of that. A mass function that depends on r, that represents the mass inside a certain radius r. And the field equation are simply that, the derivative of the mass function with respect to r is simply 4 pi r squared rho, where rho is the energy density associated with the electric field. And the interpretation of this is very clear. We integrate outward from the center, and essentially we multiply the energy density by shells of increasing area. We sum this up, and we get the mass, integrated over a certain radius. So if I make the substitution for the electrostatic energy density up here, well, we get a factor, we get rid of, some of the factors here. We get q squared over 2r squared. And I think that's correct. And what I have to do then to obtain the mass function is to integrate this. When I integrate, I'm going to pick up a constant of integration. So this is the mass within a certain radius r. This is my constant of integration, and what's left over is the integral of this, which is q squared over 2r with a minus sign. And that is an accurate description, even in general relativity, of the mass function of, the outside region, the mass function, outside of the distribution of mass and charge that will then collapse and form a black hole. And I think the interpretation of this equation is pretty clear. M, capital M, is the mass that we would measure asymptotically at infinity. M of r is the mass that we measure at some finite radius. When we go from infinity down to a finite radius, we leave out all of that electrostatic energy density that is everywhere in space-time and decays as 1 over r4. So you go from infinity, you go down to a finite radius, you leave out all of that stuff, and that means that the mass decreases from its asymptotic value to something which, exclude the stuff that you left out. And that's why you have a minus sign, and the radial dependence, of course, comes from the fact that the distribution of electrostatic field energy decays in space-time as 1 over r squared. This is something that can be understood easily, I think, on the basis of this sort of quick Newtonian argument, where you just, make sure that the mass density that you're talking about here includes all possible forms of energy in the accounting of mass. So that's why I'm inserting here electrostatic field energy. But all of those equations are, either a Newtonian type equation, but in fact, they turn out to be exact within general relativity. And all we have to do to get the metric, essentially, it's not obvious, but you can take my word for this, is to say that, well, we still have a metric that will be in the form that I displayed before with a metric function f. The only difference is that now f is not going to be 1 minus 2 capital M over r. It's going to be 1 minus 2 the mass function divided by r. And if I make the substitution, I get 1 minus 2m over r, as we would in Schwarzschild, but then I modify this by the electrostatic term. And I have an extra term in the metric. And that is the function f that corresponds to a Reissner-Nordström solution. So what you can do, I mean, you can go through the more exact calculation as I lay it out in the book. You can check that this is a valid solution to the Einstein field equations, given that your T mu nu is the T mu nu that's produced by the electromagnetic field that's associated with the presence of charge. And you can view the solution as something that holds only in the outside of the mass and charge distribution. But if you let that collapse down to a point, as or to a very small volume, such that you do have a black hole situation, then what you find is that, well, this is going to be the metric everywhere in the black hole spacetime. So what we have here is something that's very close to what we had before for the Schwarzschild metric. We still have spherical symmetry. We still have a metric that takes the usual form. But one major difference, and even the details of the solution outside the black hole are not all that different. I mean, we do have a little bit of a shift in the metric function here. But clearly, if r is very large, this extra term over here is not going to have very large quantitative effects on anything that happens outside. But where this becomes very interesting is when you start to look at what happens near the event horizon, or even deeper than that. There are rather remarkable properties associated with the internal structure of this black hole. And one hint that this is happening, that there might be a lot going on here, is the fact that here we have a quadratic function of 1 over r. F is a quadratic function of 1 over r. And that means that instead of just having 1 0 as we had before, in a Schwarzschild case, we have the possibility of having 2 zeros, and therefore the possibility of having 2 horizons. And now we need to understand what's up with that. So the point is that we have 2 zeros. There are 2 horizons, 2 places where f of r naught is equal to 0. So there's going to be 2 solutions for this. And if you work it out, you find that, well, the 2 solutions, one that I'll call r plus, is m plus the square root of m squared minus q squared. And the other one is r minus, which is m minus the square root of m squared minus q squared. In those relativistic units that I'm working with here, q has the same unit as m, and those are the 2 zeros of the equation f equals 0. The solutions are real, provided that q squared is smaller than m squared. So there's a natural bound on how much charge a black hole can actually have. So here we're going to be demanding that q squared be no larger than m squared. If we violate this, then we have a black hole that has way too much charge. And in fact, we don't have a black hole at all, because those 2 solutions become imaginary, which means that we don't have places where f goes to 0. And we're dealing with something else entirely. We don't have a black hole unless this condition is imposed.
I have another physical system that we prove to be as a physical system, and we'll ask you what the black hole.
Yeah, so this is still a valid solution for. So if we violate this condition, this is still a valid solution to the Einstein field equations. But it cannot be expected to describe a black hole. It's going to be describing the exterior of that charge distribution, which oversaturates this bound here. So it's only a black hole if you don't if you satisfy this condition, and it's only if you have if you do satisfy this condition that you have horizons. If you don't, you don't. Right. So the consequence of having 2 horizons here, well, turns out to be pretty interesting, and I want to tell you a little bit about that. And I'm going to spend a little bit of time on the Reissner-Nordström case, even though physically it's not all that realistic. It's not all that, it's not, you don't really expect to find charged black holes in the universe. Because a lot of what I'm going to say here turns out to apply also for the Kerr case. The Kerr case is a little harder because we don't have spherical symmetry. But a lot of what I'm going to say about the interior of the black hole here turns out to also be, more or less valid, with modifications in the Kerr case. So it's worthwhile to spend some time understanding this black hole, this type of black hole. By the way, I might mention that for elementary particles, this bound is certainly not satisfied. I mean, the charge to mass ratio for an electron is, 10 to the 20 or something ridiculous like that. So sometimes you hear the idea from crackpots, that, elementary particles should be black holes, but, they're not. So there's just no way that elementary particles can be black holes. Okay. So what does it all mean? What does the second horizon mean? Well, we're going to look a little bit into that. Before I do that, I just want to tell you something which is going to be relevant to the discussion. But I'm going to do this first, and then we'll have a lot to think about. So suppose we're talking about geodesic motion in Reissner-Nordström. And suppose I'm talking about motion that proceeds entirely in the radial and time direction, so that I'm switching off, angular motion. And, well, how do I produce geodesic motion in Schwarzschild? Well, the idea is that I, stay away from charged particles, because if I'm dealing with the motion of a charged particle, there's going to be an electrostatic force acting on the charge from the black hole, so I don't want to deal with that. So I'll talk about the motion of a neutral particle moving in the curved space-time geometry outside of this black hole, and it's going to be moving in the absence of forces on a geodesic of the Reissner-Nordström space-time. And well, we have our usual killing vector, which tells us that the energy of the particle, the energy at infinity is going to be a constant of the motion, so we can rely on that to simplify the geodesic equation. And while I won't go through all the details here, but you can take my word that, so here I'm talking about, time-like geodesic motion in Reissner-Nordström. You can just believe me when I say that T dot, dt d tau, I'm using proper time here as a parameter on the word line. T dot is going to be equal to E over F. That was true for Schwarzschild. It remains true for Reissner-Nordström. So that comes from, precisely, is just, an explicit form of that equation right here. And then you can use the normalization condition on the forward velocity to conclude that R dot squared plus F must be equal to, a constant energy on the right-hand side. So this equation in particular is pretty important because it has a nice interpretation as an energy equation. This is kinetic energy, this is potential energy, this is conserved total energy. And I can learn a lot about the nature of the motion by just drawing a plot of F and looking at that as an energy diagram. So if I plot F as a function of R for Reissner-Nordström, I have two places where F becomes 0. So asymptotically, F is 1. And it will go to 0 at R minus, and it will go to 0 at R plus. So qualitatively, F behaves like this. It goes to 0, becomes negative, and it crosses 0 again, becomes positive again. And then at R equals 0, it really blows up, and it goes to plus infinity. This equation tells us that if this is the value of E squared, the difference between E squared and the plot of F is the kinetic energy of the particle. And as in classical mechanics, we know that we have allowed motion if the difference is positive. So what do we conclude from this? We throw in the particle, and it falls in. And not surprisingly, it falls in below the event horizon. So we've pushed the particle, toward the black hole, so it falls beneath the event horizon. It crosses the other horizon over here. What happens here? Sorry? Does it stop or does it turn around? It's a turning point, right? It's a turning point of the motion. So it falls in. There's a turning point. It comes back out of the inner horizon, out of the outer horizon, and it goes all the way back to infinity. So this is a particle that falls into the black hole and comes back out. There's no other, there's no escape from this conclusion. It's based on this very simple equation. This is the graphical, representation of the equation, and there seems to be, no way out. Well, no, there is a way out. The particle does escape from the black hole, or so it seems. So, this is a sign that there's something pretty funny going on here. How can you go into a black hole and emerge again? Well, it can happen in Reissner-Nordström. Why is it that we have this repulsive barrier in the potential energy? Well, in standard Newtonian type situations, we have potential barriers when we have angular momentum. Angular momentum always produces an L squared over R squared type term in the potential energy. And, because there's angular momentum, there's angular motion. And the angular motion prevents the particle from getting too close to the center. That's a standard story of Newtonian mechanics. Well, here there's no angular momentum, so that's not it. There's a repulsive barrier that doesn't come from angular momentum. If there's no angular momentum, it must come entirely from gravity. And that's true. Gravity is repulsive deep inside the Reissner-Nordström black hole. And we knew that. Look at that equation. The mass inside radius r is m minus something. Could it be that r is so small that m becomes negative? Yeah. Inside r minus, you can check it algebraically, this term dominates over the total mass term. And m minus something, which is larger than that something, than m, produces something which is negative. So as you go deep into the Reissner-Nordström black hole, as you go below the inner horizon, what happens is that m of r, the mass that you feel inside a certain radius, becomes negative. Gravity becomes repulsive, and it's the repulsive gravity that pushes you out of the black hole eventually. There could be a way out. For example, it's conceivable that something funny would happen with time in such a way that the time it takes you to reach the turning point would be infinite. Well, that doesn't happen. It just doesn't happen because, there's nothing that goes infinite in this equation that might explain a behavior like that. So what I'm telling you here is actually for real. Well, not really, but I'll tell you why in a moment. It's for real as long as you believe in, as long as we're working specifically in the Reissner-Nordström metric. You have a question?
Can you just put up the argumentation there that if m of r, inside the black hole, m of r becomes negative, and you said m is becomes repulsive. So is the idea then that you have a negative mass and that is repulsive to positive masses? Where do you get that from?
Sorry?
Is that just, it's intuitively clear why a negative mass should be repulsive to positive mass. Right.
Oh, you want a better argument?
I just wasn't sure whether there was more.
Well, yeah. So here I'm sort of jumping back and forth between relativity and sort of Newtonian pictures. And if I think in terms of Newtonian terms, I could think of this as being involved, as being the active mass acting on my body. The force would be this mass times the body's mass divided by r squared. And if this active mass is negative, then the gravitational force has to be repulsive. And I was sort of using this language. I think people often do that, jump back and forth between a truly relativistic description and something which is Newtonian and not exact, but brings some intuition, and that's what I was trying to do here. So I think it's a nice little argument that sort of shows that this is strange, but that there's something intuitive about this after all. But the point is that even if you don't want to think along those terms, geodesic motion in Reissner-Nordström does have this feature of having a turning point, does have this property of having a particle that falls below the black hole that would emerge in finite proper time out of the black hole eventually. So we need to understand that. We need to play with that and try to see if we can firm this up and build a full space-time picture of what's going on. Yep? Well, that's what we need to understand, right? In what sense are they horizons if you can go through them, in both ways? Well, let's see what we can do about that. Okay. Well, we know that when f goes to 0, we have a problem with our coordinates. That's the same story as we told for Schwarzschild, and it's just the same story here. And in fact, now we understand that there are two places where this can happen. R naught, the place where f goes to 0, is either r plus, which is somewhere, is either r plus or r minus. So if we're going to build a space-time view of this, if we're going to try to improve our understanding of what seems to be be suggested here, what we have to do is what we have to understand is how to actually deal with those coordinate singularities and how, understand what happens when you try to go through each one of those two horizons. And essentially, I don't need to do anything different from what I did for Schwarzschild if we just agree or if we just realize that I can deal with each horizon at a time. I can deal with the coordinate singularities of each horizon at a time. So the way that I constructed classical coordinates before can be adapted here, one horizon at a time. And we're going to patch things up in such a way that perhaps gradually a complete space-time view will emerge for what's going on here. So let me deal first with the outer horizon. So the thing that I did call the event horizon of the black hole, the outermost solution to f equals 0. So let's deal with the r equals r plus horizon. Well, the way that I constructed classical coordinates for Schwarzschild relied only on the fact that f was going to 0 at a certain r naught radius. And I don't need to change any of those details. I can say that close to r naught, close to r plus in this case, f will have a behavior that's going to be, 2 kappa plus. I'll call it kappa plus, because here we're going to have two surface gravity parameters, one associated with r plus, the other one associated with r minus. And close to r plus, for example, the function f will be, behaving like this as r minus r plus terms, if it would be quadratic, in r minus r plus. And then kappa plus would be defined, as we had it before, as half the derivative of the function f evaluated at r plus. And that's a calculation you can do. Well, everything else follows. I mean, we still have, a u coordinate, which is t minus r star, a v coordinate, which is t plus r star. We still have r star defined as an integral of 1 over f, except that now the function f is a little bit different. And we can still, follow the recipe to construct classical coordinates from all of this. And what we're going to do is to construct a classical u, uppercase u, which is going to be e to the minus kappa plus u, and classical v, which is uppercase v, which is going to be e to the kappa plus v. So we just go through the entire recipe. And by doing that, what we get is a coordinate system that allows us to go from the outside of R plus to the inside of R plus. And essentially, the classical diagram that we get from this is identical to the classical diagram that we got for Schwarzschild. I mean, none of the big, so there's some small details that are a little bit different here, but none of the main features are altered when we go from Schwarzschild to Reissner-Nordström. So basically, the classical diagram that we would get here, let me call those coordinates u plus and v plus. We would construct a classical diagram based on those coordinates. This would be the u coordinate. This would be the v axis. And this would be, the surface r equals r plus. This would be the other copy of r equals r plus, because we're aware that each r equal constant, curve in Reissner-Nordström will be, will have two copies. This would be some r greater than r plus surface, and we have another copy here. And this would be r equals, I'll call it r equals r1 because I want to say something about this. And I'll call this one r equals r1 as well. And I just want to pick r1 in such a way that r1 is smaller than r plus, but it's also larger than r minus, because I want to avoid crossing the other horizon here. I want to really work in the neighborhood of the first horizon before I start dealing with the other horizon. In Schwarzschild, we could go all the way to r equals 0. Here, I don't want to do that, because going all the way to r equals 0 means crossing the other horizon at r minus, and I don't want to do that. In this first classical patch, what I'm going to do is cut things off before I reach r minus. So I'll use the patch only before I hit r1, or only after I hit r1 if I look at the, at the mirror, the time reversal copy of that surface. So essentially, I'm going to construct a classical patch that will do the job of going across r plus, and I'll go all the way to r1, arbitrarily selected. But I'm not going to try to go beyond that. What I'll need to do to go beyond that is to think about crossing the other horizon. And I'll do that by constructing a new classical patch, a different one. Here we have to go one horizon at a time. If I'm an observer falling into the black hole, I'm not sure if I have any colors here. No, I don't. If I'm an observer crossing the black hole, well, I do something like this. I fall in from, from over there, and eventually I cross the r plus horizon, and I'll just follow the motion of my observer up until r1, which is here. And essentially, on the space-time diagram, it looks simply like a word line that follows, that moves within the light cone, which is everywhere at 45 degrees. And eventually, I cross the event horizon, and eventually, I reach the surface. And I choose not to follow the motion any further for the time being. All right. Well, at this stage, no big surprises. We've managed to investigate the nature of the outer horizon. And this outer horizon has exactly the same features as the r equals 2m horizon of Schwarzschild. This has exactly the same interpretation as an event horizon. This distinguishes events inside the black hole that cannot send a signal to infinity versus the ones that are outside the black hole that can. So this surface over here does have all the features that r equals 2m had this morning, and therefore this is, according to our definitions, this is the event horizon of the spacetime. Okay, well, let's do r minus now and see what happens then. We have another horizon in a sense that now will have to be understood. And we're going to do something very similar, except we're going to have to change some of the details a little bit because things are a little bit different inside. And one thing that we have to sort of understand is that, well, let me draw a picture. Let's say that this is the r plus horizon. And let's say that this is the r minus horizon. Everywhere outside, well, we're outside the black hole, and in here, we're inside the black hole. Outside the black hole, f is positive. And if f is positive, that means that the coefficient here is negative, the coefficient here is positive, and from that we recognize that t is a time coordinate, r is a spatial coordinate. You know, that's an old story. In here, f has changed sign, so f has become negative. Here, the coefficient here becomes positive, the coefficient here becomes negative. And that's where we recognize that r has become a time-like coordinate, and t is now a space-like coordinate. Again, that's old news because that's exactly the same thing that happened for Schwarzschild. What is new is that as we go beyond r minus, f changes sign again. So that after crossing the inner horizon, t reacquires a meaning as a time coordinate, and r reacquires a meaning as a space-like coordinate. The nature of r equals 0 will change completely from Schwarzschild to Reissner-Nordström, because in Schwarzschild spacetime, r equals 0 was a spot where f was negative. And r equals 0, therefore, was a space-like singularity. Here, r equals 0 is a spot where f is positive. R equals 0 has become a time-like singularity. And what we're going to see in a moment is that, well, the structure of the black hole, the inside structure of the black hole is completely different. So let's proceed with that. So we have, a few details that are a little bit different here. Here, I start with an f that is negative, and it's going to go positive when we go beyond r minus. So the way I would write it out here would be to say that f is negative when r is larger than r minus, but it's going to change sign to be positive when r is smaller than r minus. So I need to adapt the equations a little bit to reflect the fact that we go from negative f to positive f, which is different from what we had before. Kappa minus, in this case, is going to be defined to be, well, minus the derivative of f evaluated r minus. So we just alter the definitions a little bit. But the rest of it, well, is exactly the same story. So we still have UV, we still have the cross-colaized version of that. The only difference is that now instead of using kappa plus, I'll be using kappa minus, which is still defined as, as a positive quantity. So this is still positive. So I don't need to rewrite the equations, you know what they look like. But what's important is the space-time diagram that it gives rise to. This is going to be a new Kruskal patch that will involve the coordinates u minus and v minus. And this Kruskal patch will start where this one leaves off. So there's going to be an r equals r1 surface over here. That's going to be the same one as the one I had here. It's going to be in the new Kruskal diagram. This is still r, so this is still a surface r equals constant, and r minus is r1 is larger than r minus. So in the Kruskal diagram, it occurs here. It has to be space-like, so therefore it's going to be here. This is r minus. This is the other copy of r minus. R equals 0 is going to be an r equal constant surface such that r is smaller than r minus. It's going to be over here in the space-time diagram. And as I said, it's a time-like singularity, no longer a space-like singularity as we had it for Schwarzschild. The fact that f has changed sign again completely changes the causal nature of the singularity. It has become time-like. So this, because here r1 is larger than r minus, it has to be that this space-like is space-like. And that's why I draw it here. It has to be space-like the same way that this surface over here is space-like. R0 r equal to 0, because r equal to 0, this r is smaller than r minus, means that this surface of constant r is a time-like surface. And it has to be drawn like this in a crustal diagram. So where's my observer? Well, we left him off here. So he's somewhere around here. That observer is going to keep on falling for a while until he crosses the r minus horizon, until he meets a turning point somewhere deeper in. Well, I don't have to do any calculations. I know that what will happen is that the observer will fall in somewhere around here, and the turning point is going to be right here somewhere. It has to be below r minus and above from r equals 0, because the diagram up there tells us that r equals 0 is not accessible to that observer. There's a turning point that takes place here because of the repulsive nature of gravity below the r minus horizon. So turning point occurs. We have another copy of the r1 surface up here. So what we're going to do is to continue to follow the motion from r1 through r minus through the turning point, back out again from r minus to r1. And on the crustal diagram, the motion proceeds up to here. And we're going to stop looking at it. I mean, we're going to give up here. This crustal patch has been used. It's, it's not going to be useful beyond r minus, because beyond r1, beyond r1, we're going toward r plus. And what we have to do is to introduce a new crustal patch that will handle the other crossing of the r plus horizon. Here's an important thing. On this diagram, we notice that we're crossing r1 twice. We go in, and we go out, and we cross r1 twice. Well, that's exactly what we see here. We have a crustal patch where we cross it once, and we cross it again. They're different. They're different r1 surfaces, and that has to do with the fact that we always have two copies of each r equal constant surface in a crustal diagram. This diagram doesn't tell us that those r1 surfaces are not the same ones. The crustal construction tells us that. Let's keep going. If we want to follow the motion of that observer, we have to keep going. We have to go beyond r1 and try to see what happens when we're about to cross the r plus horizon once more. You had a question, Seth?
Because you're moving in motion with, or in that patch, you're moving part the motion is through a patch where f is less than 0.
Mm-hmm.
Are you then considered a space-like observer?
No. No. So this observer is still time-like.
Okay.
Yeah. Let's see. So f is positive in this region. F is negative in this region. But there's no, so the light cones are still at 45 degrees, and as long as you're moving within the light cone, there would be no way for an observer to go from a time-like world line to a space-like world line to a time-like world line. That is just impossible. So the motion is forever time-like. Okay, so let's do one more patch. This is going to be another horizon crossing at r equals r plus. Well, it's the same story as what we had over there, except that now it's a distinct crustal patch, not the same one as before, another one altogether. So here I'm sort of losing, I'm losing labels, but essentially I'll just draw it without defining the coordinates. So we have the two null directions like this. We have the R1 surface, which is identified with that one up here. We have r equals r plus here and here. And what happens is that, well, over here we have, r equal constant surfaces larger than r plus, so we're safely outside the black hole when we're over here. And what happens to the observer? Well, it depends a little bit on what he wants to do here. But one possibility is to say that, well, the observer is going to do what we said he should do here. He's going to go out beyond R minus. We've covered that already, beyond R1, through R plus, and back to a safe distance again. And on the diagram, well, we left off the observer right here. The observer is going to emerge out of R plus and go off to a safe distance. So we're crossing the R plus surface again, but notice that this one is now a past horizon, not a future horizon. So the second crossing of R plus is very different from the first crossing. Here we were going into a black hole through a future horizon. Now we're emerging out of a white hole through a past horizon. There are different R plus surfaces, the same way that those were different R1 surfaces in spacetime. This, as far as we're concerned here in the outer universe, this appears as if we have an observer that just comes out of a white hole horizon. This part of the space-time here is what we normally call a white hole. It's the same thing that we had, essentially, that we had in the Schwarzschild case before. So when you take it all together, when you look at the representation of the motion right here, you see part of the information. But there's some mysteries here because we seem to be crossing surfaces that should be one-way surfaces more than once. When you actually do it more fully and construct carefully a bunch of crustal patches that allow you to go through each horizon and handle all of the coordinate singularities across each one of the horizons, what you realize is that each time you cross one of those surfaces, you're actually crossing a different one. Here, you're going into the black hole from the future horizon. Over here, you're crossing another horizon, which has nothing to do with an event horizon. It's an interior horizon. I might as well call it an apparent horizon. You go through the turning point. You reemerge out of this horizon, but it's a different copy. You go through this R1 surface again, but it's a different one. And eventually, you get out of, you get out of this horizon, but this horizon is not a future horizon. It's a past horizon. Therefore, you can get out. So every time you're crossing a horizon, which is a one-way surface, but every time you're crossing a different one, and you're crossing it in a different direction. Altogether, what you see here is the notion that it's possible to go through a charged black hole and get out into a new universe. It has to be a new universe, because if you were tempted to say that you're back in the same universe as where you started from, that would mean that after going through a while across the black hole, you would reemerge from this side and encounter yourself about to go in. Well, some people have attempted to do this, to postulate a sort of topological identification of the whole thing, and postulated that if you go through a black hole, you would reemerge, and you would build a time-like, a close time-like curve like that. Well, it probably doesn't make much sense. Not that this makes much sense, but I think it's more plausible to think that what you've constructed here is a black hole tunnel, not to the same universe, but to a new universe. And if you were so inclined, you could choose to fall into this black hole, because as you reemerge out of the white hole, you find yourself in a new universe that contains a new black hole, and you could choose to go in again and go through this entire cycle and keep repeating it forever and ever and ever. And you would explore like this new universes one after the other. Question? No question?
Can you explain one more time how you could see yourself going in if you were to promote into the same universe?
Well, if you're coming, so if you say that this whole trip will take you back to this first crustal patch as opposed to keep creating new crustal patches, then the conclusion would have to be that after going through the first tunnel, you would come out here. And if you come out there, well, you can actually propagate up to here. And who do you see here? Well, you see yourself there. Because this point in time is the same point that you end up after going through the entire tunnel. That's the essence of a closed time-like curve. You go forward in time until somehow you re-encounter yourself, before you got started. People don't tend to like closed time-like curves. They seem to violate basic ideas of causality. If you do make this topological identification, you have them. And perhaps you might, what you would like to be able to say is that microphysics or whatever the fundamental laws of physics don't allow those things to happen. But here it's really a global issue of making topological identifications in a global space-time, and there's no real strong argument that would disallow that from happening and disallow you from doing that. But my temptation is not to do that and to instead view this as something that unfolds in space-time. It's just that you go through the first black hole tunnel, you see another black hole at the end, and then you have another black hole tunnel, and then you emerge again to the other universe, and that other universe contains another black hole, so there's an infinite succession of black holes. But every time you're moving forward in time, and there's really no way you can find yourself back where you started, because those universes are in succession in time. To go back to the previous universe, you would have to go backwards in time.
What if there's someone sitting outside watching this? What are they going to see?
Sitting over here, for example?
Yeah.
Well, they would see something emerging from something that seems to have mass. They would see a horizon where nothing seems to be able to go in, because if you go in, you go faster than the speed of light. So they would see something that is normally called a white hole horizon. It has exactly the reverse properties from a black hole horizon. Everything can come out, nothing can go in. This is a gravitating body that seems to be impossible to penetrate, but that sends out some stuff from time to time. So it's a white hole, not a black hole. It's the temporal opposite of what a black hole is. It would look weird, no doubt. Yeah, that's what they would see.
How could you define time across universes? Of course, I understood it the way that you said, is every universe a separate space-time?
We have one space-time,
Different universes.
but we have a bunch of successive universes separated in time.
Right. So
Yeah.
all the universes are embedded in a bigger space-time.
Yeah.
Are they proper submanifolds? Any given universe?
What's a proper submanifold?
A submanifold, sorry.
Oh, sure. Yeah. Yeah.
But they're not connected. Well, the only connection they have is via the black hole.
That's right. There's a one-way connection from the past universe to the future universe, and no possibility of coming back. Yeah. Well, if you think that this is all very weird, you're perfectly correct. I mean, this is very weird. But nevertheless, if you believe that this is a relevant description of space-time for a Schwarzschild black hole, if you agree with me that this is an exact solution to the Einstein field equations, either this is total nonsense, but there must be a reason for that, or it's true, in which case we have to sort of live with those weird features. I'll tell you later on that, in fact, it's real in the sense that it does represent the true properties of an exact solution to the Einstein field equations. But I'm going to tell you that, in fact, if you consider perturbations of this, if you consider realistic situations that may not have the exact symmetries of the Reissner-Nordström solution, that all of that gets destroyed. Question?
I was just going to ask what happens if you create such a black hole through physical process.
Okay, let me do a little bit more along those lines, and then I'll answer this question. So in order to proceed from here, I'm almost done, in fact, and I think I have all of the essential pieces, but I think you'll agree with me that if I want to, so what I seem to what seems to be necessary here to describe the global, the global structure of that space-time is to go from one patch to another patch to another patch to another patch, and that becomes a little bit cumbersome after a while. I mean, it can be done, and it's really a valid way of proceeding. But it would be nice if, instead of dealing with separate patches, I could patch up all the things together into some mega space-time diagram that would actually represent the entire, or at least a good enough portion of the entire space-time manifold, without having to go from, in one patch as opposed to having to go from one patch to another patch to another patch. And the idea here is to do a Penrose trick and compactify all of those crustal coordinates in such a way that each patch becomes a finite patch, and then we can just really glue the patches together into one major diagram. So I'm going to draw that diagram, but you're going to see that, well, in fact, it's just patching things up in a way that sort of makes sense. So here's a Penrose-Carter diagram. Of the entire Reissner-Nordström manifold. Well, not the whole thing, because I cannot draw the whole thing. I'll draw just a significant portion of it. So I'll draw the singularities first. This is the first copy of R equals 0. This is the other copy of R equals 0. So what I've drawn here is the Penrose version of those two singularities, and they're time-like as they should be. I'm going to draw two lines like this, and I'm going to draw two lines like that. This is going to be R plus. This is going to be another copy of R plus. This is going to be R minus. This is going to be another copy of R minus. Two more lines like that. And I'm going to extend this one a little bit beyond. This is going to be another R plus. This is going to be another R plus. I'm going to keep going for a little bit, like that. This is, OK, so here's another copy of the singularity. And here's another set of lines. And, well, I think I'm going to stop here. This is an R minus. This is an R minus. And this is still R plus, R plus. This is Cry plus. This is Cry minus. This is Cry minus. This is Cry plus. This is another Cry minus. This is another Cry minus. So what do we see here? Well, let me try to distinguish each patch. So my observer started his trip from here. And the first thing that he did was to go across the event horizon here at R plus. This is this portion of the motion, which before I had to cut off over here, but now I don't have to because I've patched things up together. Then I go to that side over here. I go from R minus through, from R1, which is here, through R minus, through the bouncing point to the turning point over here, back across R minus, back through R1, and out through the white hole horizon. And that's that last patch over there. That's the complete trip through the black hole tunnel, through the outer horizon, the inner horizon, the turning point, inner horizon, outer horizon, out into the universe. In principle, I would have to draw another layer that would contain exactly the same pieces, because this observer can then turn around and fall back into the black hole that lives over here. I would have to stack this up over here, and in principle, the entire manifold would be infinitely high. There's no way I can compactify it completely. It extends from minus infinity to plus infinity on the diagram. But I think you see the essence of it. I don't really need to explicitly do all of those pieces. This is R equals 0. This is R equals 0. Time-like singularities. What's very different here is the fact that R equals 0 being a time-like place means that you can choose, while being a space, sorry, how do I want to say this? R equals 0 is a time-like world line, or a time-like place in a space-time diagram. R equals 0 is somewhere in space, as opposed to being some instant of time, as it was in the other situation of Schwarzschild. In Schwarzschild, the diagram was something like this. And really, once you're inside the black hole, there's no way you can avoid going into r equals 0, because r equals 0 is a moment in time. And you cannot avoid going forward in time. And therefore, you have to hit r equals 0 if you find yourself inside a Schwarzschild black hole. Here, the situation is very different, because r equals 0 is not a moment in time. It's a place in space. And you can choose not to go there. And therefore, there's no reason for you to hit the singularity. And in fact, if you follow a geodesic, you have a repulsive barrier. The repulsive gravity just prevents you from hitting r equals 0. And that's why, well, if you cannot hit the singularity, if the black hole doesn't want you to stay there, you have to go somewhere. And the alternative is simply to have a turning point over here, and for you to get out and emerge somewhere else, not in the same universe, into that new universe. That's, so the fact that you've altered the metric a little bit in such a way that outside is not very different, but the internal aspects of that change, the fact that you have this extra term here, which, by the way, does dominate when r is small, because you have a 1 over r squared correction here, which clearly will become dominant when r is small, is really the thing that changes the internal structure of the space-time, the internal structure of the black hole completely. So let me say a couple of more things. So you ask about, well, where is the collapsing star in all of this? Well, the collapsing star would follow a motion that's more or less like this. You would have gravitational collapse of a charged body. And that gravitational collapse would be subjected to the same gravitational repulsion that we've talked about, on top of being subjected to the electrostatic repulsion of the charge inside the star. So the collapsing star will collapse for a while, but then all of those repulsive things will be such that the collapsing star also will bounce and will start expanding once it's collapsed far enough. So essentially, the surface of the collapsing star would do something like this. It starts from over here, which is future past time like infinity. It lives at r equals constant for a while, but then it starts collapsing. It's going to go through the event horizon. It's going to go through the inner horizon. But here, everything has become repulsive. The collapse stops and bounces out. And the star also will reemerge into a new universe. So the observer that's waiting for all that to happen will see an observer coming out, and then it will see the entire star coming out, as if it's chasing after the poor observer. Everything on the left-hand side of that line is not described by the Reissner-Nordström solution, because it's now part of the stellar interior, which has a different metric. So everything on the left here can be erased. And what you have then is a space-time diagram that will accurately represent gravitational collapse and expansion of a charged body to form a charged black hole. So here I have the surface of the collapsing star. I need a word line that describes the center of this. So I'll just draw it in some random way like that. So everything in here is the stellar interior. And everything outside is the Reissner-Nordström solution. So we still have the outer horizon. We still have this inner horizon. We still have this inner horizon, this white hole horizon. So we, a lot of the pieces of the extended Reissner-Nordström manifold survive here, but we lose everything that's internal to the matter. One thing that's very interesting about all of this is that the singularity is completely outside the matter distribution. It's not the star that collapses to zero volume to form a singularity. The singularity forms for different reasons. And that has to do with the fact that, well, if you live inside the black hole right here, if you consider a space-like surface inside the black hole, you notice that this space-like surface is actually spatially closed. The black hole tunnel is a closed universe. What happens to electric field lines in a closed universe? Well, they emanate from the body, right? But they can't go all the way to infinity because there's no infinity. They have to reconverge on the other side of the closed universe. And when they reconverge, they create a singularity. So this singularity is what happens to the electric field lines that emerge out of the star. You know, that's where all the charge is. The charge is all here. And the electric field lines are, you know, emerging, emanating from all of this as they normally do. But then instead of, you know, radiating all out to infinity, they have to reconverge to the other side of this closed universe, which is that point over here. So you have, electric field lines that all go out radially from the matter distribution, but then they have to reconverge on the other side. And as they do that, of course, they all, you know, go down to the same point. And that is the physical mechanism for the formation of this singularity, completely divorced from the matter distribution in the sense of stellar matter. It's something else entirely. If this has positive charge, what's the sign of that charge? Has to be negative. We have, you know, diverging field lines over here. We have converging field lines there. So our interpretation would be that, well, we have a charge singularity with a charge that is exactly an opposite, the same but opposite to the charge that's contained here, because, you know, the charge of a closed universe has to be 0. So all of those features are, you know, there in that sort of funny black hole spacetime. Well, there's even more to it than that. I'll redraw this picture, or something. You know, I'll go back to the extended diagram because it's a little bit easier to draw. Well, this was really not bad at all. I mean, this was a little bit strange, perhaps, but let me tell you something really disturbing now. So I'll just draw a piece of the diagram so that I can focus on the important aspects. This is a piece of Scri+. This is the event horizon, R+, and this is the inner horizon, R-. This is the singularity at R = 0. The question I want to ask is this really something that can be predicted by initial data that you would place on a space-like surface outside the black hole before the black hole is formed? So here's a space-like surface that might represent, the initial moment just before the charge, the charged star was about to collapse. This is what is known as a Cauchy surface in space-time. This is where you place all of the initial data that is supposed to predict what will happen in the future. And, you know, GR is a well-posed theory, which means that if you have the right amount of initial data, which is the induced metric on sigma and the extrinsic curvature on sigma, you have enough information to propagate forward in the future to get a unique solution thereafter. So this is I0. Well, let's think about this. Suppose that I want to know precisely what should happen at a point here outside the black hole. I want to ask, is there enough information in initial data on the initial surface, sigma, to predict what happens there unambiguously, uniquely? And the answer is yes. Because if I'm at that point and I draw a backwards light cone, I find that the backwards light cone intersects my surface sigma. And therefore, there's no way that information from outside of sigma could go and upset what happens here. Everything that will happen here will be dictated by signals that would either propagate with the speed of light up to that point or propagate with speed less than the speed of light up to that point. The point is that if I know everything that happens here on this hypersurface, I know precisely what will happen there. There's no chance of external influences coming in to upset my predictions here based on the initial data there. So that's true outside the black hole. It's true also inside the black hole. If I'm inside the black hole, inside R = R+, and I draw a backwards light cone, I still see that it intersects my initial data surface, and by exactly the same reasoning, there's no way that some external, influence would come that is not part of the specification that I gave initially, and that would upset the predictions that I would make here based on initial data there. There's no possibility of having, outside influences upsetting my predictions here. Well, maybe you can see that we'll run into trouble at some point. What if I have a point up here? Well, okay, let's look at the backwards light cone. Here we're still fine. But here we run into the singularity. And one thing about singularities is that they tend to be unpredictable. I don't know the laws of physics on the singularity. I don't know which boundary conditions I should place here in order to have a well-posed unique evolution. And what seems to be happening here is that for any point that's beyond R minus, the predictions that I would make here based on initial data that I place here outside the black hole before the collapse proceeds would not be enough to tell me what happens here, because here there is a chance that something unpredictable will emerge from the singularity and upset my predictions. If I wanted to avoid a situation like this, I would have to place boundary conditions everywhere on the singularity that would tell me what's supposed to come out of there. And that would mean that I know the laws of physics there. But I don't. That's a place where everything breaks down. The singularity of the Reissner-Nordström spacetime, like the singularity of Schwarzschild, is a place where the laws of physics just break down. The laws of general relativity break down. We need something else. We need a quantum gravity theory or something like that to tell us what's supposed to happen in the singularity. So based purely on the classical field equations, based purely on general relativity, we can draw those space-time diagrams. We can think of black hole tunnels. We can do all of these fun things. But in fact, we have no confidence that this is an accurate prediction, because who's to know that the singularity is going to choose to cooperate with our, with our attempts to travel through the black hole tunnel? Who's to say that it's not going to do something so dramatic as to destroy everything that happens here, or at least change it so much that, in fact, the black hole tunnel doesn't actually pan out? The point is that in the extended Reissner-Nordström solution, even if we have a collapsing star, there's a place beyond which we have to give up hope of coming up with unique predictions. We have a breakdown of predictability of Einstein's theory up here. And that's very disturbing, because it happens well before and elsewhere than where the singularity is. In Schwarzschild, I'm not too upset about the fact that we're breaking predictability here, because I know that I'm just about to kill, to die, meeting the singularity. So the laws of physics break down here, but I'm not too worried about that, because I have very little to live for once I'm here. Over here, while I was thinking that I might actually live a very long and rich life, crossing the black hole tunnel. But the point is that I really don't know. I mean, I have no way of deciding or predicting what will happen to me once I come to view, once I come into the field of view of the singularity, or once I start to see signals, arbitrary signals, coming to me from the singularity. And this is a situation where, well outside where the singularity is, where the curvature is still well behaved, where there's no sign that locally something funny is happening, there's something global about the nature of the space-time that tells me that I've completely lost predictive power. That's very disturbing. So what I told you about black hole tunnels, well, for one thing, you cannot be confident about, because it all depends on how things proceed in the presence of a singularity about which I know nothing. But on top of that, there seems to be something much more, much more dangerous and much more, well, at least to me, disturbing about the nature of general relativity, is that not only does it predict its breakdown when you're about to encounter a singularity where all signs of meeting the singularity are apparent, for example, blowing up curvatures and things like that. Here, as you're about to cross the inner horizon, at least apparently, there seems to be no sign that things are about to go bad. As you cross the inner horizon here, the curvature of the Reissner-Nordström spacetime is perfectly well behaved, perfectly finite, perfectly bounded. You will never notice anything wrong happening locally, except when it's a little bit too late and you start seeing some stuff coming out from the singularity, stuff that you cannot predict. That spoils completely your predictive power beyond that. That to me is very disturbing. And it was so disturbing to me that I wrote a PhD thesis all about that. And, well, it turns out that I was following up on a work of all sorts of people. But my goal, my objective as a PhD student was to try to understand what's supposed to happen here. Why is it that GR seems to allow itself like this to lose predictive power? And what I want to do is to tell you a little bit about that, because it turns out there's a very nice resolution of all of this. And that resolution, in fact, achieves two things. It restores the predictive power of the theory completely, and it seals off the black hole tunnel completely. And in the end, when you understand better what's going on, what you find is that, well, there's nothing very exceptional about charged black holes after all. So let me tell you that story. I'll redraw this diagram, because there's another property of the inner horizon that I haven't talked about, which turns out to be important. So here's the singularity again. Here's the inner horizon again. Here's the outer horizon again. So this is R plus. This is R minus. Okay, and this is R equals 0. I'm not going to even think about what happens beyond R minus, because I don't know. I'm going to think of what happens before you reach R minus. So last week I was sending Stephanie down the black hole, so I'll go myself this time. So here I am crossing the outer horizon, and then attempting to cross the inner horizon, knowing, well, not knowing at all what's going to happen beyond that. Stephanie is outside, and Stephanie has a very long life, so she's outside at a safe distance, living a very long life, such that after t equals infinity, she ends up on I plus right here. This is I plus. This is scry plus. This is the word line of an observer that lives forever and end up after an infinite amount of proper time meeting I plus. As I told you this morning, we have to be a little bit careful about interpreting a point like this in the Penrose diagram, because it seems here that we're dealing with the intersection of scry, the event horizon, the inner horizon, the singularity, and I plus, and that's just an artifact of the mathematical construction. So we have to be a little bit careful about this, but anyway, that's not going to be a problem. Okay, let's assume that Stephanie sends me a Christmas card every year in the form of, a flash of laser or something like that. Well, in year 0, I get my Christmas card up here. In year 1, I get it up here. In year 2, I get it up here. In year 3, I get it up here. So the time intervals over here are equal. Every year on Christmas Day, Stephanie sends me a Christmas card. But let's see what happens. She continues to do that forever. Once a year, I get a Christmas card. Those time intervals, as far as the outside observer are concerned, are all equal. As far as I'm concerned, falling into the black hole and crossing the inner horizon, I'm getting an infinite number of Christmas cards in a finite amount of proper time. The time it takes me to go from the outer horizon to the inner horizon is finite. It might take me half an hour, or something like that if I'm dealing with a billion solar mass black hole. So, in the course of half an hour, I'm getting a lifetime, not just a lifetime, but an infinite amount of Christmas cards. Because Stephanie lives on forever, and every year I get a card. As far as she's concerned, I'm getting a card every year. As far as I'm concerned, I'm getting an infinite number of cards in 30 minutes. That's not pleasant. Because, the amount of energy that might be sent in toward the black hole might be very small. We could be careful and choose the frequency of the laser light to be such, or the amplitude of the laser to be decaying in time, so that I don't actually feed an infinite amount of energy to the black hole. Nevertheless, as I observe what's coming to me, I see everything that comes during the entire duration of the universe within a period of 30 minutes, while in fact within a period of a few seconds. Because it's all happening as I'm about to cross the inner horizon. And in fact, what we're starting to recognize here is that the inner horizon is a surface of infinite blue shift. Everything that happens in the outside universe forever, for all times, will be perceived by me as proceeding in a highly accelerated rate at a speed that, in fact, becomes infinite as I'm about to cross the inner horizon. That's a source of violent instability inside the black hole. You can have very gentle processes taking place in the outside universe. Very, very gentle, falling off in time, very gently. Yet when you're inside the black hole, you see all of that in an accelerated time period that becomes infinitely blue shifted as you're about to cross the inner horizon. And the bottom line is that, unless you work forever in the outside universe to preserve all of the symmetries of the Reissner-Nordström solution, in particular spherical symmetry and the fact that it doesn't depend on time, this is impossible to guarantee, of course. And as soon as you switch on a slight perturbation, which will appear very slight outside, will not perturb things much outside, that perturbation will be strongly amplified as it propagates inward toward the black hole. That perturbation will, in fact, blue shift itself off. It will pile up on the inner horizon. And any measurement of what happens, from the outside, any measurement that I would make inside would come with an exponential blue shift that would turn a finite amount of energy into an infinite energy density as perceived by me and perceived by any internal observer. Bottom line is that as soon as we switch on a perturbation, you force the creation of a singularity on the inner horizon. Completely different from that singularity. That's an externally caused singularity. All of this piling radiation that I'm talking about here, as I was able to show in my thesis, will manage to form a curvature singularity right there. That singularity is null. It's not space-like as in Schwarzschild. It has a different character. And in fact, it's formed by different processes. It's not a singularity that happens because R goes to 0. It's a singularity that happened because the internal mass function blows up to infinity. You get all of that stuff compressed into a very short time. You get infinite densities piling up onto the inner horizon. And that corresponds to the internal mass of the black hole as measured internally, not externally, internally, blowing up to infinity. And, my supervisor and I called that a mass inflation singularity. Inflation was, sort of, well, still fashionable, but it was fashionable at the time, and that was a way of, of piggybacking on that term, so we called it mass inflation singularity. But this achieves two very important things. First of all, it tells us that space-time actually does not proceed beyond the inner horizon. As soon as you see a singularity, you're done. Space-time is done. And falling into the charged black hole, you'll meet the mass inflation singularity, which qualitatively is pretty much the same thing as falling into this type of singularity. You will not survive encountering the singularity, so space-time, as well as you, stop here or stop here. So you form a singularity before you actually reach the inner horizon, which means that everything to the future of that is not part of the actual space-time. You seal off the black hole tunnels, but you also remove any place in the space-time where you might have violated, the predictive power, where you might have lost predictive power, because now you lose predictive power because you explicitly encounter a singularity. That's like what we have here. We lose predictive power, but we see that curvature is blowing up. We see that a singularity is about to form. It's not like the old situation where there was no local sign that we were about to lose predictive power. So the formation of that singularity achieves two things. It achieves the fact that, well, those black hole tunnels are really an artifact of a solution which has a lot of built-in symmetries. And relaxing those symmetries have, very mild effects outside, but extremely serious effects inside. And in fact, as soon as you relax the symmetries a little bit, as soon as you allow for time-dependent external processes, which always will be there, you create the singularity, you block off the black hole tunnels, and you restore the predictive power of the theory up to the formation of that singularity. And that, I think, is a very nice resolution for all of those very disturbing features that were noticed before. So I was quite proud after my PhD to have been able to say something about this. I mean, I shouldn't claim too much credit because the suspicion that you would form a singularity here had been made a long time ago by Penrose back in the late 60s. What no one had done seriously before is to actually construct a solution to the Einstein field equations that incorporated all of that, the flow of stuff along the inner horizon and the back reaction, solving the Einstein field equations for this influx of matter, and something, construct a solution that would reveal the formation of a singularity through this mass inflation formalism. That's what I was able to do for a PhD. So the ideas were sort of identified beforehand. We were able to flesh it out and construct a more complete, description of what was already suspected. So I see lots of questions. So you had your hand first.
Say we completely ignore all the other stuff outside that's being sent in. Would your own presence be enough to form it?
Well, that's the beauty of it. Even if you say, okay, let's all agree outside to keep things really, really quiet forever, my own presence would create the disturbance that would then produce that.
So that's what would happen for, like, say, a body collapsing.
Right. So in more realistic terms, if you have a collapsing star that has a little tiny perturbation on it, it's not perfectly spherically symmetric, that perturbation will become dynamical during the collapse. And it will it will produce a time-dependent process outside the black hole. Those waves that are generated by the collapse will in fact backscatter off the space-time curvature, will be reflected back in, and will pile up on the Cauchy horizon. So anything you can conceive will in fact produce exactly this, this singularity. So it would be impossible to protect yourself against this. And as you said before, even if you thought you did everything right, you going in is enough of a perturbation. It would produce enough of a gravitational wave outside the black hole that would then come into the black hole, propagate through the black hole to produce the same instability. So no matter what you do, you're doomed. There were other questions. Steph, you had a question? That was it? Yeah.
Similar, but now you just confused me because you just said it seems like your argument doesn't need the observer to live a long life anymore for the instability to be.
No.
So why did you?
Because it's simpler to explain like that. So a realistic version of this would be to say, this is me falling in. This is me emitting a tiny, tiny, tiny amount of gravitational waves. Those gravitational waves will go out to infinity, but then eventually they'll meet a little bit of space-time curvature and they'll be scattered back in. This is extremely gentle. Outside, we would never be able to measure this. It's so tiny. But part of the gravitational waves that don't make it all the way out to infinity would actually be scattered back into where the black hole, and they would exactly do what I said. They would pile up on the event horizon. I call it Cauchy horizon for technical reasons. But they would pile up over here. I would see exactly the same blue shift effect, and my own gravitational waves would kill me in the end. That could be my own gravitational waves, or it could be, you know, electromagnetic waves or gravitational waves that would be produced by the collapsing star as it's collapsing, and I fail to preserve all of its symmetries. Or it could it could be you in the outside universe blowing your nose or something like that, create a tiny, you know, amount of gravitational radiation that would do all of that stuff, but eventually pile up onto the Cauchy horizon. There's a violent instability inside the black hole that eventually will produce the singularity, seal off the black hole tunnel, and save GR from losing predictive power. You have a question? Yes, except that now, you know, I have to do all of this in a time-dependent context. So, it's a different function that now will start depending on time as well, and it blows up, you know, as I proceed in that direction.
So, because you said the singularity doesn't form because of r going to 0, but because of mass going to infinity.
Right.
Given that we still have a, well, then of our end of time, dependence of n, isn't there still an n going to 0 as part of, well, isn't r still going to 0 as part of n going to infinity, given that we still have the dependency?
That we still have what, sorry?
Given that we still have the dependence of n from r.
Oh, okay, yeah, so the r dependence survives, certainly. And if there was a place in here where r is 0, the mass, the mass would blow up there. But the point is that there's nowhere here. Here, there's nowhere where r is equal to 0, because in fact r is bounded below by r minus. So in the actual situation, there's nowhere inside the black hole except, well, there's a little bit more to it than that, but essentially in this portion here of the space-time diagram, r is always bounded below by r minus, and there's no opportunity to reach r equals 0. It's not just part. It's not part of the actual manifold.
What becomes of the what you said at the very beginning, that for this n of r, mass is negative and thereby gravity attracted to something similar happens in structure, or you get rid of it as well?
Yeah, so here it's, let's see, so I would have to try, yeah, so it's still happening. So I didn't draw it very carefully here, but, you know, so if we go back to the extended diagram, the collapsing star still does something like this. My trajectory inside the black hole is something like this. So the bounce is still taking place, and the pileup takes place all the way over here. So this is the new position for the singularity. But before the collapsing star, gets a notice that the singularity is formed, it still had time to bounce. And as I proceed inward, I still also had time to bounce before I actually come across the inner horizon singularity. So this branch of the inner horizon, nothing happens there. It's really this branch. It's only this branch where things happen, where things go singular. So a lot of those features are still present, but they don't. You don't go all the way to the formation of a tunnel and the new universe and all of that stuff. You had a question? Yeah. The Riemann tensor? Yes. So the Riemann tensor is really, or even better, the square of the Riemann tensor is really a very good indicator of where the singularity happens to be, because it's a scalar quantity. You don't have to worry about whether it's a coordinate artifact or something like that. The Riemann tensor for any space-time like this, which is spherically symmetric, apart from numerical factors, tend to go like m squared over r to the 6th power. So there are two ways you can produce a curvature singularity. Either you go where r is equal to 0, or you have an increase of the mass. You have a mass inflation singularity. So the curvature will blow up because the mass diverges, not because r goes to 0. So yes, so because here we have this condition taking place on the inner horizon, we find that it corresponds to a curvature singularity. Yeah. Mm-hmm.
Assuming simulation of black holes, collision of charged black hole.
Mm-hmm.
In this case, we have to consider electromagnetic force.
Sure. Yeah.
But we define the mass like that, and then we don't need. I think we need to consider electromagnetic force.
Okay, so here it depends. So instead of talking about the collision of two black holes, we could think of the motion of a charged particle in Reissner-Nordström. So in everything that I've done, I was thinking of the motion of a neutral particle so that I didn't have to worry about the electrostatic interaction. If we have an electrostatic interaction, if we have a charged particle interacting with a black hole, then, well, depending on the signs of the two charges, either I have an attractive force or a repulsive force, and I would have to take that into account. But in typical situations, what you find is that, well, the electrostatic interaction doesn't dominate over gravity. So what I said about geodesic motion is more or less what would happen even in the presence of an electrostatic interaction. If we have the collision between two black holes, so here we have an interesting possibility, and in fact, in the next homework assignment, you'll explore this a little bit. If you have two black holes of equal masses and of equal charges with a charge to mass ratio equal to 1, and if the charge of this black hole is opposite to the charge of that black hole, you have a possibility of balancing out gravity against electrostatic repulsion, and you have the possibility of creating a situation involving two stable black holes, which will not move unless you disturb them. If the charge is less than the mass, then gravity will win. And in fact, the merger of the two black holes, even though it will be influenced by electrostatic repulsion, you will still merge, and it will still form a larger black hole. And yes, you do need to take into account electrostatic repulsion, the electrostatic interaction to get everything right. But more or less qualitatively, it doesn't make a huge qualitative difference. I don't think anybody has attempted to do that, though, to actually simulate the merger of two charged black holes. It would be interesting to see how that goes. Yep.
Is it possible to, if you have opposite charges, so the black hole has an opposite charge to the matter coming in, could you get a written equilibrium so that the attractive force of gravity and the repulsive force of the charge directly cancel and the particle just stands still?
Yeah, it is possible, and in fact, it's exactly the mechanism that prevents you from trying to overcharge a black hole to turn it into something which would not be a black hole and would in fact correspond to a naked singularity. So if you think, okay, let's say we have a black hole of a certain charge Q, which is barely smaller than its mass, then you say, okay, no problem. All I have to do is to throw in an additional charge, and I will saturate and oversaturate the bound, and my black hole is going to be forced to turn itself into a naked singularity. But the point is that if you're doing that, you're fighting about your charged particle has to, so you have to add to the charge, which means that you have to add, the charge with the same sign, right? So if you're trying to add a positive charge, the initial black hole is already positive charge, so you have electrostatic repulsion, and the point is that at some point, if you want to really make sure that the charge penetrates the event horizon, you have to send it in with a lot of energy to actually overcome the electrostatic barrier, repulsive barrier. And if you do that, well, you're also adding energy to the black hole, and you find invariably that as you try to add charge, you have to add mass also. Otherwise, the particle will just bounce out. It will not be able to penetrate the event horizon. It will be forced by electrostatic repulsion to turn its way, to turn around. So that mechanism is exactly what prevents you from ever hoping to overcharge a black hole and let it turn into a naked singularity. That's essentially a way of stating the third law of black hole mechanics. I'll talk about that next time. But the third law of black hole mechanics says that, well, what it says in words is that it's impossible to conceive of a physical process, well, there's a little bit of fine print, but it says essentially that it's impossible to reduce the surface gravity of a black hole to zero in a finite sequence of operations. What I didn't tell you is that the surface gravity of the Reissner-Nordström black hole, defined in the usual way, is something that would go to zero if we had what is called an extremal black hole where charge matches m. Well, no need to go into the details, but the point is that, a statement of the third law of black hole mechanics is precisely the statement that, that you cannot possibly saturate this bound in a finite sequence of operations. That would, imply that you can reduce the surface gravity to zero. And, well, there's a very solid proof that this cannot happen in general relativity unless you violate all sorts of energy conditions and things like that. There was another question, yeah?
Why does back reaction of mass inflation does not change the signature of singularity? I mean, you mean the singularity is always in this case.
Okay, you're forcing me to give you a little bit more detail. So as best as we could find, based on all sorts of different models of what's going on here, the picture is something like this. So we have the outside of the black hole. We have scry. We have the outer horizon. We have radiation. So let's say I have a collapsing star that forms the black hole. If we remove all the symmetries, if we allow for a slight perturbation outside, we have radiation that comes off from the collapsing star. But it continues to emit, the star continues to emit radiation while it collapses. And in fact, the smaller it gets, the faster it goes, the more dynamical the situation is, the more radiation it comes out. So there's really a lot of radiation that comes off the collapsing star as it continues to collapse. Part of this radiation over here gets backscattered by space-time curvature, and instead of continuing to be outgoing, it starts to come back toward the black hole, and it becomes incoming radiation. It's that incoming radiation that piles up onto the Cauchy horizon and eventually turns it into a null singularity. But that's not the end of the story, because what happens also is that this singularity is also acquiring part of that radiation that continues to escape from the collapsing star. And essentially that tends to, so the inner horizon singularity started out at some finite value for the radius, r minus, but the process of absorbing all of this extra radiation that continues to be emitted from the collapsing star means that, in fact, the mass inflation singularity is shrinking in r. R decreases as you follow the singularity into the future. So r becomes smaller and smaller until you reach a point where the singularity is shrunk to zero-size singularity, to a r equals 0 singularity, at which case it connects up with a space-like portion of the singularity. So to the best of our understanding, the black hole singularity, and that would be true also for a rotating black hole. We did all of this work for Reissner-Nordström because we could rely on spherical symmetry and make models about this. But to the best of our understanding, the black hole singularity in the general case has a space-like portion that corresponds to r equals 0, and a null portion that corresponds to m equals infinity. And those two portions are distinct in the sense that one is clearly space-like, the other one is clearly null. And I'm not sure exactly what happens at the corner there, and that's not something that our models can actually deal with very easily. But it would be nice to actually, well, I mean, some people are trying to, well, some people have said that they would like to simulate this numerically to see what happens. And I'm waiting for that to happen. And I'm looking forward for a time where, you know, there's going to be some serious numerical investigation of what happens there, because it's a rather interesting, you know, phenomenon what goes on there. So, so did that answer your question? Yeah. Well, I don't think I'll do Kerr today. I'll have to do Kerr next time. I think that's pretty much all I wanted to say about Reissner-Nordström and more. Thank you for your questions. That was a lot of fun for me. It's rare that I get to, you know, to recall the early, you know, the glorious days of my PhD thesis. So thank you for giving me the opportunity of doing that. I can still take some questions if you still have some. But if you don't, we can quit now and do Kerr next time. All right, so I'll see you next week.